good.
Okay, so slide number 9. We've had our 2 types of energy, our 2 main forms. We have kinetic, which is all about motion, and we have potential, which is like stored up energy or energy that something has because of its position. Obviously, gravitational potential energy, which is the calculation, the equation that we were using last week, that's all about positioning. Where is the object in reference to the reference, the frame of reference, right? That usually the ground, possibly the countertop, tabletop, or whatever situation you're talking about. What we're going to do now is kind of look at how these forms can transfer back and forth, because something that's in motion doesn't stay in motion forever. Something that has height doesn't stay at that height forever. It probably gets in motion and starts to move downward, or maybe it could even move upward. So there has to be this kind of understanding as you go from one form to the other. We said that they are basically inversely proportionate. Whatever one does, the other is going to do the exact opposite. So if kinetic goes up, potential goes down. If kinetic goes up, then that means potential has to go down. So there's going to be that reverse. Whatever one's doing, the other is going to do the opposite. And so one of your vocab terms is energy diagrams. And so with an energy bar diagram or an energy diagram, you'll kind of hear it called multiple things. It all means the same thing. It's basically showing the amount of energy that you have in an object by the vertical position using these different bars. Okay, kind of like, almost like bar graphs in a way. Each bar is going to represent a type of energy. Okay, and so in the bar chart, we're constructing a bar for each form. So for kinetic, for potential, and then there's also going to usually be a third one, which is going to represent the total energy in the system. The length of the bar, or how much of that bar is shaded in, is going to represent the amount of energy that's present. So it's just a way to represent the energy. Obviously, the bigger the bar, the more it's shaded in, the greater the amount of energy that it has. Okay, so this is what it might look like. We have our KE, which is our kinetic, we have our PE, which is potential, and we have our TME. It's not misspelling time, leaving the I out. This stands for total mechanical energy. So this is the total energy that's in the system, and it's represented. What do you notice with each of these yellow bars? Charlie?
They're all full.
They're all full. They have the same amount. So this is the total energy in this specific system. We don't have a number associated with that right now. It's just kind of looking at it in general. But the total mechanical is going to stay constant, because you can't destroy energy and you can't create energy. So that means the total energy in a system is going to stay constant. What does change is the forms. What does it switch back and forth to? So if you look at position A, this is the diagram representing that location. B, C, D, and E, obviously. The easiest thing for me, at least, and usually for everyone else, I look at height first. If you have the most height in the system, so like at position A, which one of our equations has height in it? Does the kinetic equation or does the gravitational? Which one had that variable of height? GPE or KE? GPE. Yeah, the GPE dependent. So if you have all height, that means that's where you're going to have all potential energy. If you're at the highest point in the system. So we don't care outside of the system. So we're looking very specifically, so like at this roller coaster, or, you know, at a pendulum, or, you know, at this specific thing that we're looking at, that's the energy. Now, is there energy around it and in other areas? Sure. We're just saying for this specific situation. So in this situation, at location A, that is the highest. That means that's where it's going to have the most potential energy. So if you look here, this bar is totally full to match our total. It is at the top. It is hanging there, waiting to start moving. If it's not moving, then that means you have zero kinetic energy. Because if your velocity is 0 anything times 0 is 0. So if you plug 0 in for velocity into that 1/2 mass times v squared, you're going to end up with 0 for your kinetic. So all potential, 0 kinetic. And then I go to kind of the opposite way of thinking. If I'm down here at the very lowest position, which is position D, I have absolutely no height. If you plug 0 height into the mass times gravity times height, what do you get? 0 height calculated in there gives you how much GPE? Well, 0, right? Yeah, so you at position D, you have absolutely no potential energy. You're at the reference point or the ground or whatever that is. So if you look here, there's absolutely no potential energy. And so that means it has all kinetic at that point. And so that's why this bar is totally filled up. And then you have the ones in between, right? You have the highest and the lowest. Those are always easy because you know one of them is going to be all kinetic and one of them is going to be all potential, depending on if you have all height or if you have no height, right? In these examples, you can visibly see height. You can't really see motion. So I always try to tell you, look at height first, because that you can actually see. And so if I have 0 height, then that means I have 0 GPE, and so everything would have to equal kinetic. All right, so height is the one that's the easiest to visualize in these examples. All right, we do have a few little ones where they actually go in motion, so that's kind of nice. You can see the motion, but you know, on these still images, you can't see the velocity. So you can see the height, so use that. And then from there, B is my second highest, so it's going to be my second greatest height for my potential bar. And then whatever you leave open for the potential, it has to be made up for in kinetic. Because if you take the red and stack it on the blue, it has to equal the total. Same thing here. If I take this and stack it on my blue, it's going to equal my total. Because again, we have to represent that that energy is not disappearing. It's not going away anywhere. Okay. So B is my next highest. That's my next greatest height for my bar. Same with C. It's kind of the middle. And then E, we have just a little bit of potential, and the rest would have to be kinetic. So it's not too hard of an idea once you kind of orient yourself and recognize what you're seeing. This can also be shown with circles, okay, so it doesn't have to be bars. And so they can be they look like pie graphs or circle graphs, and it will also show the type of energy. Obviously, there's no separate circle for the total. The circle itself represents the total, just like we use a circle graph to represent like the percentages. We assume that 100% is the whole. And so if you have all of the energy, it's represented by a filled in total circle. And then from there, you kind of divide it in colors to represent the two different types of energy. And so obviously the percent filled in is going to match the type of energy that you're trying to represent. And the greater the percentage of the circle filled in means the greater amount of that particular type of energy that you're trying to represent. Okay? Makes sense? All right, I'm going to need you to get 2 different colors out. And they don't have to be like this pink and blue. They can be if you want. If you want to use highlighters or pens, that is fine. If you want to get my colored pencils, there's some by the window. Highlighters, pens, colored pencils is fine. But you need 2 distinct colors that you can use for the next couple of examples. We only have 2 freshmen absent today. John and Reagan. Zigger. But if I have to guess, she'll probably come in later. Okay, so have your 2 colors. first thing I want you to do, when you get your colors chosen, you have a little box in the bottom right-hand corner. It says PE equals and KE equals. I want you to put the color that you're gonna use for the PE and just put a line, like you can color it with it. And then for the KE, do the same thing. That way when you're looking at this, you can orient yourself with what color is representing what type of energy. If you just have two colors, but you don't use that key to tell you, you can get yourself confused, okay? So just like this, potential energy is this color, kinetic energy is this color. I want to show, I might have to go back over here and do it. There we go. All right, so this is going to show you the motion that's involved, and then we're going to go back and kind of do frame by frame and fill this in. So this is the same exact system that you guys have in front of you. We're going to look at this step by step. Watch, here's my circle, here's my 100% of the energy that's in this system. They're using the same colors, we have this pink and we have the blue, and it's going to also show the velocity here. So I'm going to do it step by step. So notice how it's gaining potential energy as it reaches the top. It's at the highest point in this whole system, right? It's all potential. It is not moving. So we have zero kinetic energy. So if you think of that, if there's no motion, you always have zero kinetic. If you have all height, or if you're at the highest point, you have all potential. So you're going to fill your circle in, your first circle, where it's all of whatever color you chose for your potential. Again, make sure that you have that key marked so you know which color represents which type of energy. So this is position A. Now, we're going to go down the hill. What do you think is going to happen to the potential as you go downhill and lose some height? It's going to go down, right? So watch. And if it's going down, then what are we going to have to gain? Kinetic. All right, so watch as we do that. Right? It's almost at the very, very bottom, and so there's just a little sliver of potential left. You want to make just like a tiny little sliver of potential, but the rest is going to be your kinetic. So as it's down there, it's in full motion. I hadn't stopped it. All right. Now we're going to go to step 3, where we're going to start going back uphill. So if we're going back up the hill, we're going to anticipate that we're going to be gaining some more of our potential, which we show here as pink. So we should gain some potential, gain some pink, lose some blue. And 3 is just a little bit above the reference point, so it's kind of like a slice of potential now. Just a slice of that potential. So we're gaining height again as we move to step 4 or position 4. So if we're gaining height, we should be gaining potential as we go up. So we should be getting more and more of the pink as we go. Now notice, it's a little bit bigger. Basically we have a kind of big slice of kinetic, but the majority is definitely that potential. You can't have more potential at position 4 than you had at position 1, because position 4 is a smaller height, it's a lower height. So there's that direct relationship between the height and your potential energy. The more height, the more potential. The less height, the less potential. ever ridden a roller coaster and you're clicking up, 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 isn't there that moment where you feel like when you're at the top, like you're frozen for a second, like the motion stops? Like, it's been a while since I've been on a roller coaster, but I can still feel that feeling really clearly. Like you get to the top and like right before your car starts to go downhill, you have that moment where you're like kind of frozen or suspended, it feels like.
Still be a little bit of kinetic energy in number one because it has to move forward to get down the hill.
So at the split second before it actually changes and starts going down, there'll be a moment when there's not. Could you make the argument that maybe there's just a tiny fraction? Possibly. But for what we're looking at, we can assume that there's not. The other feeling, if you're on a swing, when you're swinging and you're at the highest point, doesn't it for just a second feel like you're almost frozen before you change and start heading back down? So every time you're at the highest, it's like, and then you have that feeling of coming back down. So again, can you make the argument that maybe there's a little bit of motion? Possibly. But if in our case, we're going to assume that it's all potential when you're at that highest. And if you can, imagine, remember that feeling of being on that swing. You're at that greatest height right before you transition and start to come back down. You feel that moment of like hesitancy where you're frozen there. Yeah.
I went on my very first roller coaster back in 2021. It was the Iron Dragon.
That was the first one. You picked a big one to start with. Did you like it?
Yeah, but I did feel a bit scared most of the ride.
Yeah, you should. They're scary. I mean, fun scary, but yeah, very cool. So you've had that feeling. Okay, so now 4 is going to come back down and we're going to end up at position 5 here. So here we're going to assume that we reach the absolute bottom. So 2 was pretty close to the reference point, but they're saying 5 is even a little bit lower than 2 was. So we're saying this is our reference point. The very lowest part of this track is basically like ground zero. So we have absolutely zero height, which means we're having all kinetic at that point. So we have all motion. And then to finish, we're going to go up a tiny little hill. So we're going to gain a little potential. So we're going to have to add in a slice of our potential. And again, you just have to have, if you're looking at your slices, like you have to have all potential, then you have to have a lot of potential, and then you have to have a little less potential. So it doesn't have to be perfect, but it has to be kind of proportionate based on the height. So this is the highest, the medium, and then the lowest. And so, looking at your slices of potential, it should represent that. Okay, I'm going to show you this without stopping it. I'm going to go back and just let it kind of play. You can watch this as it's kind of a more realistic transfer as it goes. So here we go. We're gaining all this potential. Okay, I'll show it one more time. Highest point. Lowest for just a second. So you can see that transfer. So kind of visually lets you recognize that. So this is back to what you had on your page. There's mine, pretty, right? Gorgeous. I know you guys are impressed. Keep your same colors. And we're gonna look at this same kind of setup, but with the bars instead. Now this one doesn't have a third bar for the total mechanical energy. Obviously, it would make sense to add in that TME or that total bar, and it would be its own separate color, and it would always be all the way filled up, okay? And then the other bars would have to equal that amount. Right, so if we look here, again, I'm gonna go to the highest point and fill that in. So if we look, this one is almost to the top, but not quite. So I'm gonna leave a little piece missing from the potential, and I'm gonna give that little piece to the kinetic. And then these, this one, it looks like it's gonna be the lowest, it's just a little bit lower than this side, and so you're gonna have just a little potential, and the rest will be kinetic. But again, the blue should stack on the red, and they should be able to fill up that bar. You can't have, where you're leaving a gap, I guess. So whatever you have here for the potential, it should stack up and fill that kinetic bar. This is almost full, and then the red fills it. You guys didn't know you get to color today. So again, looking at height is usually the easiest way to visually see what's going on. Obviously, these are not moving, so it's hard to see the motion, but we can visually see the height. So I always pick either the highest or the lowest to start with and kind of work my way from there. Any questions on these? You feel pretty good? Honestly, the hardest part I think is just keeping the color straight. Not on like the extreme ones, but like these kind of middle ones. Like, okay, making sure I'm, still pretty close to the top, so making sure my potential bar is gonna be my bigger color, and then, just whatever I have left, make that my red. Okay, if you borrowed mine, go ahead and you can put those back. We shouldn't need them anymore today.
No.
Cole,
Give me the highlighters.
don't be difficult.
Yeah, give me the highlighters, please.
All right, so what we just looked at is really demonstrating a big idea in physics, that energy can never be created or destroyed. We heard this on a few of the videos. The amount of energy that's in our universe right now is the same amount of energy that's been in our universe for billions of years. It is set. What it can do is go back and forth between a lot of different forms. So it's not that the energy can't move or can't change, can't transform, but the total amount is set. All right, so we can't create any more energy and we can't get rid of energy. And that is called the law of conservation of energy. And so we can't ever lose energy, even though we say that. And I'll try to catch myself, but it's easy to say, where did that energy go? Or, how is it changed? That's the way I'll try to say it. But a lot of times it's easy to say, okay, that energy was lost. It's not really lost. It's just not in the same form as it was. Okay. This is called, looking at the total energy in like that roller coaster system, is what we're going to call the TME, or the total mechanical energy. And that is the sum of the kinetic and the potential in that system. So TME is the total energy for that system. Obviously, we have a TME, the total energy that's in our entire universe, but that would be a little overwhelming. So we look at things very small, a very small situation, or a diagram or something. And so we have some really common forms of energy transfer, and one major one is looking at friction. If there would be no friction, so in outer space, maybe like on ice, you can get things reduced where there's almost no friction. The total amount of energy in a system would always just balance back and forth between our kinetic and potential. It wouldn't ever seem like it goes away. It does seem like energy disappears or is destroyed or lost because of friction, which makes sense. If things are moving, then there's gonna be that friction involved. And so the motion seems like it slows down, and it's not because that energy is lost, it's because some of that energy then gets transferred into friction. So if we get rid of friction, then there'd be like this perfect conversion of kinetic back to potential, and nothing would slow it down, and it would just continue on and on and on. But we know that that's not the case. So again, this is showing with the bars, kind of like what it did with the circles, where the green is our total mechanical, and it's stationary, it's not changing. So at the highest point, you're all potential. Now it's gonna go down, and when it's at the very bottom, you have all kinetic and no potential. Now you're gaining potential, now you're losing potential, right? And you can see as that cart gains and loses height, it gains and loses potential energy, and then obviously kinetic is directly affected by that as well. So in this system though, we know that some of that motion energy, some of that kinetic energy between the wheels and the track, that's gonna transfer into friction. And so really we'd be losing a little bit of that kinetic energy to friction. It'd be transferring into friction whenever you have anything moving. Because let's face it, it's really hard for us to find a frictionless system or environment. And so what is the side effect a lot of times of when things move past each other or that friction? Well, yeah, think about it. That's why we rub our hands together. It doesn't take very long rubbing your hands together and you get that thermal energy or heat. So that's what heat is. It's the movement of those molecules rubbing past each other. And so that's why moving parts a lot of times will get hot, right? That mechanical or that kinetic energy is transferring into thermal energy. And so that heat is kind of the byproduct of that. So remember the relationship, when we talked about this when we looked at states of matter, right? The more those molecules move around, the more their temperature is increasing. So temperature is really just a measure of that kinetic energy or the motion of those molecules. Okay, so again, in a perfect physics world, a person could jump from a diving board and hit the water with the exact same amount of energy that they had at the top. So you have all potential, now you have all kinetic, as you have zero potential because you have zero height, right? So 10 joules of potential, 0 of kinetic because he's not moving. Then as he starts to fall, that starts to switch, and now we have 0 potential and all kinetic. But we know that that is not exactly a realistic way of how things happen. Because energy is transferred from potential to kinetic until that diver hits the water. But in the real world, you're going to have air resistance. That's a form of friction. In the problems that we do, we ignore friction because, and you won't later on, but just because we're at the beginning and getting the basics. But we have to always understand that we're simplifying that because really there would be frictions involved. Also, as the diver hits the water, some of that kinetic energy is transferred into a little bit of heat as that body like pushes past those water molecules. Also, what do you hear when a person splashes into a pool? Yeah, the splash, right? You hear the splash. Not only do you see the splash, you hear it. Sound is a form of energy also. So some of that kinetic energy also then transfers into sound. So you've lost some to friction, you've lost some to sound. And again, I'm saying lost because you're losing some of that kinetic energy, but it's really not gone, disappeared. It's then just transferred into that thermal and sound. So however the total energy of the diver never changes, the energy of the system just transfers throughout that potential to kinetic and then to heat and then a little bit into sound. Now again, it's just a little bit for thermal and it's just a little bit that transfers into sound, but that little bit accounts for the kinetic energy that seems to be gone, or the kinetic energy that seems to be kind of missing. Okay. And again, I'll do a little demonstration probably tomorrow where we'll look at a marble rolling down a track, and you'll see what happens to that marble, if it goes all the way up to the other side, or if it only makes it partially up, and we'll look at that and try to explain it. Oh my gosh, Mr. Edmonds. Let's end with Mr. Edmonds today.
No, but I should.